Welcome to Spring LIB.
Hi there. Today we're talking about a mass on a spring. In this problem, we're given the velocity equation for the mass on the spring, but we're not given the position equation. And we're asked to find the period, the maximum amplitude, the maximum acceleration, and the spring constant. So the first thing to do with this is to realize that an equation that we do know is the standard equation for the position with regards to time in this case, which is going to be x of t is going to be equal to the amplitude times the cosine of omega t plus phi. Now, this isn't exactly what we want, but we want to get to the velocity equation so that we can compare the two. So to get from position to velocity, we just take a simple derivative, and we get v of t is going to be equal to negative a omega times sine of omega t plus phi. Now this looks a lot more like what we have over here. And actually from this you can pull out a lot of stuff. You can pull out the amplitude and the angular frequency, which we can use to get the period that we're looking for. So if we come back over here, let's look at problem A. Problem A asks for the period t. So from this we can kind of see that omega is just going to be 4.71. We just look at this omega right here. It's exactly the same as this. So t is going to equal 2 pi divided by omega, which is going to be approximately 1.33 seconds. Always important to have that unit. Looking at problem B, we're looking for the amplitude. So over here, we're looking at the amplitude right here times omega is going to give us negative 3.6. So we're looking for negative 3.6 is going to equal negative a times omega. We know that omega is 4.71. We have this 3.6. Some simple math can tell us that the amplitude is going to be equal to 0.76. And the problem specifies that this amplitude right here is in centimeters. So we're going to, or centimeters per second rather. So we're going to call this centimeters. Excellent. So now we're going to go on to problem C. Problem C asks for the maximum acceleration. We've got a great expression for position and velocity, but we don't yet have one for acceleration. So we'll write that down, and that's just going to be another derivative to get from velocity to acceleration. So we have acceleration with respect to time is going to be equal to negative a omega squared cosine of omega t plus phi. Now this acceleration term is going to be maximized when cosine is equal to -1, because cosine's range is from -1 to 1. And we want to cancel out this negative here. So we can say that A max is going to be equal to A omega squared. Plugging in, we get that's about equal to 16.86 centimeters per second squared. We get the centimeters from here. We're still using the same units. And then the 2 omegas give us the over second squared. The final part of the problem asks for the spring constant. We have an expression for spring constant. So omega is going to equal the square root of k over m. We have omega from right up here, this is 4.71. We have the mass up here. You really just have to rearrange and then plug in. So this is going to lead us to k is going to equal the mass times the angular frequency squared. And that's going to be just about 11.1 newtons per meter. And that's really how you do this problem. I hope that helped.